So, welcome you here. We are going to do a presentation. Well, Stefan Masufre is going to do a presentation linked to his chair of excellence. He's spending here in the university a couple of months this year and 1 month next year. And among these, included in this stay, is giving this presentation. So, just to present Stefan. Stefan is Researcher Director of the French National Research Center, the CNRS. After graduating from the School of Engineering and the University of Limoges in France in Material Science and Plasma Physics in 1996, he received a PhD in the field of low-temperature plasma physics in 2001 from the Technical University of Eindhoven in the Netherlands. His research activities are linked to spacecraft electric propulsion, where he began working in 2003 after joining the ICAR laboratory in Orleans. Currently, he's the head of electric propulsion team at ICARE. He's also the director of the Oracle Joint Laboratory between ICARE and ExoTrail. It's a startup working in the field. His research interests cover the Hall thrusters and different variants of the Hall thruster, and also new electric propulsion concepts and micropropulsion. His research also extends to physics and technology of hollow cathodes and the physics of magnetized discharges. He's especially recognized for the development of laser diagnostic, and he has authored more than 110 scientific publications and 130 conference proceedings. During his career, he has received several prizes, as the Bronze Medal from CNRS in 2008, or the Noah Hershkowitz Award from the Institute of Physics in 2012, and he's also a senior member of the American Institute of Aeronautics and Astronautics, and a member of the board of directors of the Electric Propulsion Rocket Society. Recently, he received he was awarded the Chair of Chancellor from Universidad Carlos III, and he's here to work in laser spectroscopy for applied to electric propulsion. Okay, so I'm going to leave him start. One thing that we are going to ask you, if you don't mind, he prefers to remove the mask. Okay, we have some margin from the people, from the audience, so in principle we are allowed to do it if everybody agrees. Okay, it's fine. So, Stefan.
So I'm here today to talk about laser spectroscopy applied to electric propulsion. So I will start my presentation directly. So this is the content. Oh, sorry, I was too fast. This is the content of my paper today. So I decided to split it in two main parts. The first part is the laser spectroscopy and laser induced resonance spectroscopy. So this is more or less 3/4 of my presentation today. But I also wanted to introduce scattering technique at the end, and especially Thomson scattering, that is very important for the field of electric propulsion and also for the field of plasma physics in general. So I will give a few words about that at the end. So I will start with that. This is probably obvious for everybody, but I would say that in the field of electric propulsion, and not only the field of electric propulsion, we need data, we need experimental data, and to be even more precise, we need experimental data at a microscopic level. Okay, I'm not talking here about thrust, ISP, mass, volume. No, we need data at a microscopic scale. Why is that? Because first we need data to better understand the physics at work. That remains ill understood nowadays, even after 60 years of research. We need data to improve. I really have a problem with my microphone. It's not fixed. My hair are too small. We need data also for improving physical model and numerical simulation outcome, to make them more reliable, to make them to give them some predictive capability. And of course, we need also data to improve the performance of the current technologies, to develop new concept, new technology for new mission profile. Okay? So, okay, we need data, and I think we all agree on that, and this is true for most of the field of physics. So, to acquire data, to record data, we need instruments, we need diagnostic techniques, okay? And Well, this is more or less a personal viewpoint, but I decided to divide instrument in two categories, two types. Okay, you have intrusive techniques and non or weakly intrusive technique. Okay, so intrusive technique means that you're measuring, in fact, a perturbed state of the medium. Okay, you don't have direct access to the real state of the medium because you have strong interaction with the instrument, so you have disturbance. Okay. So that makes life a bit complicated because you have to account for the disturbance you are introducing in your medium, okay? And this category of instrument include electrostatic probes, Langmuir probes, RPA, E-Crosby probes, and so on, and also mass spectrometry and other type of technique, okay? In contrast, we also have non-intrusive or weakly intrusive technique, and if you look at the list I give on the slide, they all are based on the use of light, in fact, okay? So this includes emission spectroscopy, absorption spectroscopy, imaging and photography, of course, and also laser-aided technique like laser spectroscopy and laser scattering, okay? And so in the talk, I will focus on the last two techniques that are weakly intrusive, as you will see. So that means that we more or less probe the real state of the medium we are interested in. So why using laser? It might not be very obvious. Because this light source has unique and excellent properties due to a very high spatial and temporal coherence. Okay, so this is a very specific light source. It has a very low divergence. You know that it's really a beam of light with a small divergence. The wavelength can be very well defined, so we can reach picometer, or even we can go below that. Or on the other hand, depending on what you want to do with your laser, it can be also extremely broad. Okay, this might be interesting for absorption spectroscopy. The time resolution is excellent because now in the field of quantum physics, they can go to attosecond or even below. So it can be extremely accurate on the temporal viewpoint. We have a high energy, high power density. Keep in mind that nowadays we reach terawatt. We have terawatt laser pulse, so that's really huge, and even more than that. So this is also interesting for some technique. And finally, we have wavelength at disposal ranging from the soft X-ray to the very far infrared. So it opens many, many, many possibilities, okay? What are the advantages of the laser-based technique? So they are non or weakly, as I will show you, they are weakly intrusive. We have a very high spatial and temporal resolution, which is very good when we are interested in studying the dynamics of a given system. It's spaces and state, I mean energy state or quantum state selective, so you can really probe a desired state for desired spaces in your medium. And we have access, as we will see, to many, many quantity from the fluorescence, or from the light that we collect either from the fluorescence process or from a scattering process. So I will start with LIF, and during the last 5-10 minutes, I will switch to scattering technique. So laser-induced fluorescence spectroscopy. This is the basic energy diagram of LIF that probably most of you know already. So we start with an absorption process. So we use laser, we use the light, we use the photon of a laser to transfer population from a low energy state, a high state in this example, to a higher energy state. And of course, the photon wavelength or photon energy has to perfectly match the energy gap between those two states. Okay, so we transfer population from a low state to a high state. So we reach an excited state, and we wait. And after some time, as you know, this is an unstable situation, so the state will de-excite, emitting light. And in fact, we capture the light. And this light that is emitted is called the fluorescence light. And all the information from the starting state, from the high state, is contained into the fluorescence light. So in addition to that, you also have non-radiative processes that are called quenching. The state can de-excite due to collision without emitting light. Okay, so you have to account for that. But in our medium that are relatively at low pressure for electric propulsion plasma discharges, the quenching phenomenon is not so important and can be neglected. So this is a basic configuration, basic scheme for LIF. So it's relatively simple on paper. So this is a general equation that describes this technique. Okay, so here I consider the total number of photons collected after you have excited a given state. So there are two things I would like to emphasize on here. First, as you can see in this equation, there is the density of the lower state. So that shows you that by measuring the fluorescence photon amount, you have access to the density of the state. That's something that can be, of course, of great interest. But there is much more than that. The most important quantity in this equation is the absorption profile, the called P absorption in this equation. The absorption profile is a distribution of the energy of the lower state, as we will see, and all the information about the system that you are probing, that the particle you are probing, is contained in this term. So what we want to do, in fact, when we do LIF, is that we want to access this absorption profile. Because you can derive, as we will see through many examples, we can derive many, many quantities from this absorption profile. So this is what we want to examine, in fact, okay? So now I will explain you what is this absorption profile and which type of information you can access by looking at it. Oh, I was too fast. Sorry, okay. Before we go on with the absorption profile, I just want to tell you that I was a bit quick when I described this energy scheme, of course. In fact, in reality, it's a bit complicated. As you know, first, you cannot do whatever you want. You have to follow some quantum selection rules. That can be very complicated, but it offers many, many possibilities. But very often, some transitions are forbidden, as you know, okay? That means that it's very difficult to access the transition and to excite the transition using a photon. So what we often do in laser spectroscopy is that we look at the rules in general, not only the rules you have studied in university, the dipole-dipole selection rules, but there are many other types of rules. And some rules are very interesting in the sense that they tell you that if a transition is forbidden with one photon, it might be allowed with many photons. So maybe with 2 photons or 3 photons or even more photons than that, okay? And very often in LIF technique, to excite a state that is of interest for us, especially the ground state, because this state is the most populated state in a low pressure, low temperature plasma, instead of using a single photon transition, we use a 2 or 3 photon transition. So this is an example of 2 photon transition. That means that the transition I consider here, this is for the xenon atom. It's very difficult to access the ground state with single photon, so we can use 2 photons. And this technique is called TALIF. You might have heard about it. It's 2 photon absorption laser-induced fluorescence. So very often, instead of using 1 photon, we use 2 photons, and we have to look at by looking at the selection rules. You can also, there are also some tricks using some quadrupole or octupole selection rules to be able to access very, very forbidden, strongly forbidden transition. And that's also what is interesting when you use laser, because lasers are high-intensity light beam. That means that they contain many, many photons. So even if the probability that you excite the transition is very, very small, because it's forbidden or even strongly forbidden, you might have enough photon in your laser beam to excite the transition. It's just a matter of probability at the end. That's what quantum mechanics tells you. So those are the main 2 schemes we use in laser-induced fluorescence spectroscopy in our field, either using 2 photons or a single photon scheme, okay? It does not change the rest. If you look at the equation, the master equation is more or less the rest. You have the density of the first state, and you have the absorption profile included, okay? So whatever the technique, single photon, multi-photon, at the end you want to measure or to have information about the absorption profile, okay? So, concerning the absorption profile, if you imagine a single atom in a perfect environment with no interaction, no other particle, no interaction with the quantum vacuum, nothing. It's not possible, of course, but if you could have that, it would mean that energy level would be perfectly defined, extremely well defined, okay? It would be infinitely narrow. The energy would be very well defined. That means that the transition, of course, between 2 levels would also be extremely well defined. So if you look at the energy distribution, which type of photon, which energy do you need to excite the transition, the result would be a Dirac delta function, because everything would be perfectly well defined. So the transition, the distribution function for the transition, in terms of energy of photon you need, would be a Dirac delta function. Unfortunately, we are not living in a perfect world. There are many, many types of interaction with the medium itself, but even without a medium, with the quantum vacuum. So you have interaction with the quantum vacuum. That means that the energy levels are not perfectly well defined. They are boxes like I show in this figure, okay? They have a given thickness in terms of energy. That means that there are, in fact, many possibilities to excite the transition in terms of photon energy, okay? So this is what we call the natural profile of the transition. There is a natural distribution function in terms of photon energy that you can use to excite a profile, okay? It will never be a Dirac delta function. There is a given profile. It's a Lorentzian shape. It has a given width. If you go far in quantum mechanics, you can show that the width is related to the lifetime of the level, actually. So the lifetime of the level gives you the width of this Lorentzian. It's quite narrow. It's in the picometer range. So you might think, whoa, but we can look at it. In fact, we can measure it, okay? So this is the natural line shape of any type of transition, whatever the transition you consider, the quantum number, the number of photons you need. It will always resemble, this distribution is always a Lorentzian function, and you cannot avoid it, okay? So this is a term, this is the absorption profile, actually. This is the natural absorption profile of your transition. But on top of that, it's a bit more complicated, of course, you have broadening mechanisms. So if nothing would happen, if you would be in a perfect vacuum and only have interaction with the quantum vacuum, you would measure this profile. But in a plasma discharge, you have particles, other atoms, molecules, charged particles, electric field, magnetic field. So you have strong interaction with your surroundings. And because of that, you have broadening of the natural line profile. So you've got the Doppler broadening. I will talk about it later. You have also what we call time-of-flight broadening. This is due to the interaction between the laser beam and the particles. You have pressure broadening due to collision, due to the van der Waals interaction. Although in our medium, the pressure is relatively low, so I would say below 100 Pascal, usually you don't have to account for this pressure broadening, so we can neglect it. I will come back to the Stark broadening at the end. This is due to electric field. And there is also an important phenomenon I want to mention, it's power broadening. So your laser beam can artificially broaden and modify the transition profile. So we will start, I will describe the Doppler broadening and power broadening because in our experiment, this is, I would say, the main two broadening mechanisms you have to consider to define the absorption profile. So the Doppler effect, well, the Doppler shift, you all know about it, so I will be very, very quick. You know that if you have a moving atom with a given velocity vector v, with respect to an observer, and if it interacts with an electromagnetic wave with a wave vector k, then you will have a frequency shift. The wave or the atom will see a different frequency, okay, not the frequency of the wave itself. So this is called the Doppler shift. So the frequency difference is called the Doppler shift. It depends on the velocity, as you can see. And so you have two possibilities. You can be blue shifted. So the shift, you are shifted towards the low wavelength, so to higher energy, or you can be red shifted. Okay, you are shifted to the larger wavelength. Okay. So if an atom is moving, you will illuminate it with a laser. Okay, there will be a Doppler shift, so the transition will be slightly shifted, and you will be able to measure the shift. So you will shift the natural profile. Okay, and the Doppler shift gives you the velocity. But in a medium, there are many, many, many particles. There is a global thermal motion of your system. So in fact, you have to account for the velocity of each particle and the thermal speed of each particles. Okay. So at the end, because you have a large group, a large number of particles, you have to account for the shift given by all the speed. Because when you do a measurement, in fact, you probe, you do not probe a single atom, of course. You probe a group of atoms, so you have to consider all the speed. So at the end, you have to consider the Doppler shift because of all the velocity. And if you are in equilibrium, you know that the velocity distribution function is a Gaussian. So you will measure a Gaussian profile on top of the Lorentzian profile that is a natural profile. So this is the Doppler effect. This is called Doppler broadening. That means that you will always measure, if the Doppler effect is dominant, you will measure a Gaussian function if you are at equilibrium. Okay, so this is now the absorption profile becomes Gaussian. Most of the time we can neglect the Lorentzian part. The shift of the center will give you the mean velocity of the group of particles you are probing. The width of your profile will give you the temperature, so the mean kinetic energy. Okay, so that's how we can measure, if we are able to measure this distribution profile. Okay, so the Doppler profile, if the Doppler effect dominates, you have access to the mean velocity, you have access to the temperature, but on top of that, you have access to the state of your medium. Because you will measure a Gaussian profile if you are in thermodynamical equilibrium. But if you are not, and I will show you many examples, you will measure a different line shape. And the shape of your profile, the shape of the velocity distribution function, will give you very accurate and precise information about the state of the medium. So that's also how you can access to information about departure from equilibrium. So in our plasma, in most of the electric propulsion devices, this is the dominant phenomenon. So you should be able to directly measure the velocity distribution function, thanks to the Doppler broadening. Another important aspect, so we'll not go into details here, but if you use too much light, the pumping rate, the rate at which you transfer the population from the lower state to the high energy state, will be very, very high, much stronger than the relaxation state, relaxation rate, okay? And this will cause a very strong coupling between the states, and that means that you strongly disturb the group of particles you are probing, in fact, because of that, okay? So if you look at the figure on the left, what it means basically is you create a hole in the velocity distribution of the particles you are probing. So if you do that, you are not really weakly intrusive or non-intrusive anymore. You strongly disturb the medium. So the hole is called a Bennett hole. So you transfer, if you prefer, you transfer too much particles in the upper state. And as a result, you have a dip in the population, okay? Because you cannot establish an equilibrium quick enough, actually. You really create a hole, you disturb your distribution function. You cannot see the hole, and you cannot probe this Bennett hole if you have a single laser. But if you have two laser beams counter-propagating, you can measure this hole, especially when they overlap at the center, when the two beams overlap at the center. The dip is then called a Lamb dip. And in fact, if you do that, you are able to totally remove and cancel out the Doppler effect. What you probe now is the hole. Okay, you see only the hole. The hole is the width of the hole is a natural line width. So basically what you see is the natural line profile, not the Doppler broadened profile anymore. And you can use this type of effect to do what we call Doppler-free LIF spectroscopy. It is very, very useful for some type of measurement when you want to be extremely accurate on the energy transition. In our case, we don't really have to use it. You could be a bit more precise on the velocity, on the center of the profile, but we are already so precise because we can have accuracy in the meter per second range. So in our case, it's fair enough that we don't use this type of spectroscopy, but you can cancel the Doppler effect and do Doppler-free spectroscopy using the fact that you strongly disturb your medium. But it has another effect. You have to be very careful with that and not too much saturate your transition. So you should not use too much laser power. Since you are modifying the distribution function, in fact, what you do is that at one point, because you make holes, in fact, so you depopulate the population of the original state. That means that you will see that at one point, when you increase the laser energy, when you increase the power density, the signal decreases. Just because you disturb more and more the medium. So you have to be careful to stay in the linear regime, not to be in the nonlinear regime. And if you push it even further, you can make the medium fully transparent. So at one point, the laser beam can just go through a medium without being absorbed because of the strong coupling between the two quantum states. So we have to be careful. That's always something we have to check when you do LIF spectroscopy. You have to be sure that in the medium you are probing, in the condition you are using, you have to be in a linear regime, to be sure that you are not disturbing the velocity distribution function or the profile you want to probe, because this is really the quantity of interest. So advantage of LIF, that will be quick. It's weakly intrusive if you do it correctly. You can select spaces and even an energy level, as I mentioned already. We have a very high spectral resolution. That's why we can really resolve the line shape, the line profile, and have information about the velocity distribution function. We have a good spatial and temporal resolution. And it is also a very sensitive technique. We can go down to 10 to the 14th per cubic meter. So it's good enough for us, I would say. But there are many limitations, so life is not perfect again. It's an incoherent process in the sense that fluorescence light is emitted in 4 pi steradian. So the signal is relatively weak in a small solid angle where you collect it, okay? If you want to measure absolute number density of the low energy state, you need calibration. Okay, you don't have directly an absolute number, you have to calibrate your system, and this is relatively complex. I will not describe all the technique here, but this is very difficult to obtain accurate absolute number density. Relative density number are automatic, but if you want an absolute number, it's much more complicated. Yeah, I just told you in the introduction that we have light available from the soft X-ray to the far infrared. Well. Not on the shelf, unfortunately. So in fact, what you can find usually is you have laser available from the UV, blue UV, up to the infrared, near infrared. Now, if you want light in the VUV, XUV, soft X-ray, or far infrared, you have to do it yourself. So there are some non-linear optical techniques that allows you to convert photons and to generate photon in the VUV, XUV. I did that in the past. It's extremely cumbersome, very difficult. So, but it exists. So nowadays, basically, you have light available down to a few tenths of nanometer. So you are in the X-ray up to tenths of micrometer. It might be difficult, but it's possible and feasible. We have many parasitic effects. Especially you have to be careful with absorption of photon. You should not absorb the photon of your laser before they reach the volume you want to probe. Same is true with the fluorescence photon. They should not be absorbed. Quenching, that means the excitation due to collision, is also important. Luckily, in the plasma discharge of electric propulsion devices, most of those effects are very weak and can be neglected. But it's, for instance, not the case for people working in the field of combustion, where the pressure is very high. So collision, for instance, is very important for them. Absorption of the light also. And finally, you have to, because we want to measure the absorption profile, we have to be able to sweep the energy, to scan the profile. So you need a tunable laser source. So it's also more complicated to have a tunable laser source than a laser source giving a laser at a given frequency, but they do exist. Nowadays, we have laser diode, we have quantum cascade laser, we have OPO system, and so on. So there are many types of laser that give you the possibility to scan the laser over a relatively broad range. It's not so broad, but broad enough to be able to access to the entire absorption profile. Example of LIF setup now. It looks like that. So basically, you have a laser. So it's one of our systems. So you have a tunable diode laser. You need something to measure the wavelength. So here I'm using a wave meter, but there are other techniques. Usually we use a Fabry-Perot interferometer to check the quality of the mode of the laser. This is important, of course, to have a nice laser beam profile. So we have to check that. And then you have various types of optical components. This is the scheme for generating photon in the UV to be able to do 2-photon absorption in the UV. probe, I don't know, krypton, xenon, oxygen, hydrogen. So it's a bit more complicated. You have a first laser that pumps a second laser. The second one is tunable. So usually you start in the infrared, you double it, you are in the green. With the green light, you pump the tunable dye laser. The dye laser is a liquid state laser. In the red, so at the end you have red at 615 nanometer. Then you double it using some nonlinear crystal. And then you mix the blue with the red, and in optics, if you mix blue and red, you have UV. This might not be obvious, but it's because of energy conservation. So you end up with a UV light at the end. In the around 200 nanometers, you are in the VUV, and you can use those photons to excite the ground state of many types of atoms. But this is already a bit more complicated. So this is the photograph of this nice system to generate photon in the UV. So you see, I don't have a laser pointer, but the white box is the solid state laser used to pump the black box that is the dye laser. And you mostly see the green because the eyes are very sensitive to green, actually. The two boxes that you see on the optical table, the gray boxes are the boxes that contain the nonlinear optical crystal, and at the end, if you do this correctly, you end up with a nice beam with millijoule of UV light, coherent UV light. This is an example of optical bench we are using with a diode laser. The blue box is a diode laser. The black box on the right is the wave meter, so used to accurately measure the wavelength, because you have to know where you are, actually, to be sure that you excite the right transition. You have a set of optics. You see also some optical fiber here on the table that are used to transport the light towards the measurement location. And the big white box that you see is the monochromator we use to examine the fluorescence light. So this was the optical train used to generate the laser beam that you need, and then you need a detection branch. So you need optics to collect the fluorescence light. Okay, so there are many ways of collecting the light depending on what you want to do, the resolution you want, and so on, the type of medium you are probing. And then what you do, of course, you are only interested in the fluorescence light, not the rest. But as you know, plasma emits light over a very broad range of frequency, so you have to get rid of the rest. So you need a filter unit, and behind the filter unit, you need a light detector to be able to convert photons into electrons, and finally you measure a current. Okay? So there are many types of light detectors, and again, the type depends on the application. So how to get rid of the spurious light and how to improve the signal? The first things you do is that you do active filtering. So you really filter actively with a filter then the light that is not of interest for you. Okay. So basically you have a filter that is a bandpass filter that is centered on the fluorescence frequency. Okay, and that will just remove the rest. Because typically the width of the fluorescence profile is picometer, relatively narrow, but the plasma will emit light from the UV to the infrared. Okay, so this represents hundreds of nanometers. And you are only interested in a very narrow window, which is about picometer width. So first you have to get rid of the rest. But even if you get rid of the rest, it is not sufficient, because on top of the fluorescence light, you have natural photon emitted at the same frequency, or the same wavelength. So you have to get rid of those photons too. And for doing that, we use passive filtering technique. Okay, so you can do on and off detection. You can use phase-sensitive detection by modulating the light beam and so on. So there are techniques that allows you to only collect the real laser-induced fluorescence photon. So you remove the natural fluorescence photon. So now I give you an example of line shape. So the left one is line shape of 10 with 2 photon LIF on a xenon atom in the plume of the reed thruster. So the profile you see here, in fact, is not the distribution function, it's the laser profile. Because in that case, the laser is wider than the absorption profile. So in fact, you measure You measure the laser profile, but it's interesting anyway because it will not change the Doppler shift. So you can still measure the Doppler shift, and if you are interested in density, you will still have access to the density of the atom you are probing, although the laser profile dominates. On the right, you see the fluorescence profile of xenon ions in a metastable state in a whole cluster. So you might think that we are not in equilibrium because it's not a Gaussian. There is a clear wing at low wavelength, but not at all. We are in perfect equilibrium here. What you see is due to the line transition, to the structure of the line. When I show you the scheme, I just draw two states. But in fact, the energy diagram could be much more complicated than that because of many effects. So you can have many sub-levels that you have to account for, and each sub-level gives you a line, in fact. So here you see the fact that xenon and isotope, and because you have isotope shift and hyperfine structure. So in this transition includes 21 sub-transitions, in fact. So if you want the true velocity distribution function, you have to deconvolute with the real transition. It's another example. This is an atom, xenon atom in the SPT 100 Hall effect thruster along the channel axis, from the inside to the outside. Again, this has nothing to do with the thermodynamical state of the medium. We are again in equilibrium. What you see is the real line shape because of the many components of the energy diagram. Okay, but we can deconvolute it when it's known. Here is an example of calculation. So this is the same transition, metastable xenon atom. We can reconstruct the line shape if we know all the quantum numbers and constants, so it's possible. I've done this work with my colleague Eva Pavelek from the University of, I don't remember the name, it is somewhere in Poland. I will find it back. She's an expert in that. She's doing atomic physics. What is interesting is that, as you know, in most of our discharge, we have a magnetic field. It's the case for whole thruster, the case for helicon, ECR, and all magnetic nozzle thruster. The fact that you have a magnetic field will disturb the energy diagram of your particles, of the transition you are probing. Again, the magnetic field will degenerate the states and create sublevels. That means that if you are able to probe the sublevels and to measure the energy shift of all the sublevels, you have a direct access to the magnetic field. So that's what we have done here. And we were able to reconstruct the line shape, as you see, relatively accurately, including the magnetic field effect. And the only tunable parameter was the magnetic field. So this is one way to measure in situ magnetic field with an accuracy which is, this is not the line you should use for doing that. You should use another transition that is less disturbed, but I think we can have an accuracy in the range of 1 Gauss. So it is extremely accurate. So to probe, for instance, magnetic field induced by the plasma itself. So that's an example of what we can do with LIF spectroscopy. So now we can measure the velocity distribution function if the Doppler effect dominates and if you do not disturb too much, saturate too much your transition. So this is an example of, this is argon atom, or argon ions. No, it is argon atom. On the axis of a cascaded arc plasma, you see here the true distribution function. And this is not a Gaussian function, but at 2 locations. So here it gives you information about the state of the medium. And you know that close to the exit you are not in equilibrium. This is due to the electric field that is generated. And also you see that you have a change in shape of the distribution that goes from a fast one to a slow one. So you start with a fast one at equilibrium, and then you end up with a slow one at equilibrium, and you see the transformation in between. This is what is happening through a shock wave. So here you are able to probe the change in the velocity distribution function when you move across a shock wave. So this can be extremely accurate, and this can be compared with numerical simulation, of course. Another example, it might be a bit more complicated to see when you're not used to it because it's a contour plot. This is a distribution function of xenon ion in a whole thruster. Behind the exit, 0 refers to the exit plane. So first you see a main beam. This is the main group of ions being accelerated in the static electric field. Then labeled 2, you have a secondary beam. That's the beam coming from the opposite side of the thruster due to the fact that we have an annular geometry. Of course, the two ion beams will interact, and you see the effect. So you see ions coming from the other side. And you have two other groups at much lower velocity. They are due to local ionization and charge exchange collision. So you can be very precise. And again, this is a very interesting information from numerical simulation, because basically numerical simulation should be able to reproduce that if they account for all the phenomena. So this is again another example of what we can do when we combine LIF with numerical simulation. This was to explain the flow of neutrals in a Hall effect thruster. Of course, I've been describing 1D measurement, so measuring in one direction with one laser beam, but you can combine laser beam. So you can have 2D measurement with 2 laser beam, 3D measurement with 3 laser beam. So if you do a 3D measurement, you have directly the whole distribution function in a 3 direction of space. You can also use more laser beam and probe the space phase, really the space phase. It's more complicated, but you can also directly do measurement in the space phase. This is an example of recent measurement by the group of Ben Jones in Michigan in a magnetic nozzle. 0 refers to the throat, and they measure it's a 2D measurement, so you see the velocity vector of the ions in the magnetic nozzle, and you see the acceleration of the ions, and also the fact that gradually the ions align with the magnetic field lines. So this is an example of what we can do. Very, very useful when you are working with magnetic nozzle and trying to optimize magnetic nozzle. Sorry. Another example of measurement performed by Onera many years ago. This is the vector plot of the velocity of cesium atom at the exit of cesium FIP thruster. So you clearly see the flow of atom. So again, this type of data, of plot, is very interesting when you want to optimize your thruster and when you want to compare with numerical outcome or better understand the origin of the performance. So now I will end this presentation on LIF by electric field measurement, because in plasma physics, electric fields are of great relevance, of course. So can we probe electric field? Yes, we can. And there are 2 ways. First way is an indirect way, the easiest one, or the easy one. In fact, you directly measure the field from the velocity distribution function of ions. So, of ions, you need charged particles, of course. You can do it directly from the most probable velocity if you assume that the medium is collisionless. So it's up to you to be sure that this assumption is correct. If this assumption is not correct, then you can use the Fried equation or the Boltzmann equation directly to retrieve the velocity distribution function and then to be able to compute the field, because you have included the electric field contribution in the Fried equation or in the Boltzmann equation. So we have done that in the past. It works pretty well. We wrote a paper a few years ago about the comparison with the 4 techniques. Of course, the 2D, 2V Boltzmann model is better, but it requires more data, and it requires 2D LIF measurement. But if you look at the discrepancy between the measurement, well, in our case, this is the plasma of a whole thruster, it might be different in another type of plasma for another type of thruster. Using the most probable velocity is good enough, I would say. We have an accuracy which is in the plus or minus 10 to 15 volt per centimeter, so I say it's probably reasonable. But we can do much better than that. We can be more accurate, but it's more complicated. And also we can be more accurate, but much more important, in the technique I will show now, there is no assumption at all on the medium, which is of course much better. We can use the Stark effect. So what is the Stark effect? This is the disturbance of an energy diagram due to an electric field. Again, because you have an electric field, this created an electrostatic force, and again, energy level will be splitted in many sublevels. All that depends on the quantum numbers, of course, but this can be calculated. It's very well known nowadays. So again, if you are able to measure the shift of energy, or the energy difference between all the sublevels, you have a direct access to the electric field. It's very similar to what we do with the Zeeman effect. With the Zeeman effect, you measure the energy difference between the Zeeman level, and you have access to the magnetic field. With the Stark effect, you measure again the energy difference, and you have access to the electric field. Okay? If you try to do that classically, you will fail, because the Stark effect, contrary to the Zeeman effect, is very weak. So you need a state that is very sensitive to external electric field. So, in fact, you have to move to what we call Rydberg state. Rydberg states are highly excited states. They are super far away from the nucleus, very close to the ionization limit. So if you prefer, they have a very high principal quantum number. So you are already at the limit of the ionization. Quantum number can be as high as 50 or 80, so you're very, very far. But you are really far. If you do some quantum calculation and you calculate the orbitals, you will see that you are very far now from the nucleus, so you have a very big atom, in fact. Okay? Since you're very far from the positively charged nucleus, you are very sensitive to external electric field. Okay? So first, you have to go to a Rydberg state, you probe the Rydberg state, and you have access to the electric field through the Stark effect. Well, I think there is only one group in the world that is able to do that. So, experimentally speaking, it's cumbersome, difficult, challenging, but it's really nice. So first, you have to go to a Rydberg state. You cannot go directly to a Rydberg state because you need the X-ray. So you see that they go in two steps. First, they have a two-photon process. They go to a excited state already, but with a low principal quantum number. And then they use a second laser to go from this excited state to a highly excited Rydberg state. Okay, so you're very far away now. So you might think, okay, I'm done. Now I look at the fluorescence. I will have the line profile, and I reconstruct the line profile. I can be able to measure the Stark shift. No, unfortunately. Rydberg states have a very long lifetime. They are very stable. Naturally, they can be easily de-excited by collision, but naturally, they have a very long lifetime. That means that the fluorescence yield is extremely small. So you will not be able to measure your signal. Okay, so it does not work. So you have to be tricky. In fact, what you do is that instead of looking at the fluorescence from the Rydberg state, either you look at the fluorescence from the intermediate state, that is depopulated, in fact, so you will see deep, or you use, if you want to be very accurate, you use a third laser to probe the transition between the intermediate state and another state. And you will be able to, when scanning the transition, to reconstruct what is happening in the Rydberg level. And you are able to measure this very complicated line shape, and then you have access to the field. So this technique is extremely accurate, around 1 volt per centimeter. There is, as you can see, no assumption, but it is so complicated to build. But it has been applied successfully to many types of discharges, especially RF discharge, RF shift, and so on. It works very, very well, but to the best of my knowledge, it has never been applied to a thruster. It's really complicated to build, so probably easier to move our thruster to their lab than building this setup. But this is how you can access the field. So basically, if I make a quick summary before I move quickly to the scattering technique, if you are able to probe the absorption spectrum, that's what you want. You have access to density, velocity, temperature, information about the thermodynamic equilibrium, magnetic field strength, and electric field strength. It's not bad. If you have all of that, I think we can improve the model and the theory and our thruster and systems. So now what about light scattering technique? Because you can simply do scattering, So there is no direct interaction when you do scattering. It's really scattering of light or scattering of a wave onto a particles. This is the energy and wave vector diagram. So the black one is the laser wave vector. Okay, so this is direction of your laser. You look in the red direction, and many people think, okay, so I probe the red direction. No, what you look is the blue. What you look at, what you measure is what is happening in the blue direction. So you have to be very careful, and it's a bit tricky when you build your setup to be sure that you probe the direction you think you are probing. You have to be very careful with that, okay? Also you look at the light in the red direction, you really probe the blue one. This is simply due to energy and momentum conservation, if you apply it to this scheme. If you look at the power that is scattered, again, the power depends on the density. So doing laser scattering, you have access to the density of the particle also. And it's independent of the state. Okay? So you have access to all the states at the same time. And there is a very important factor that is the so-called form factor that also gives you information about the velocity distribution function or the state of your medium. So this is also the parameter you want to probe, in fact. So there are many types of scattering. So you have Rayleigh scattering, that is the easiest one, the one that always occurs. It's an inelastic one. Simply, that's really the scattering of a wave without interaction with the particles. So it's always present when you do this. Even when you do LIF, you have scattering, of course. Huh? So this can be, depending on what you do, this can be disturbing. You have inelastic scattering. You might have heard about it. This is so-called Raman scattering. In that case, you have interaction with the particles, and it depends on the rotational and vibrational quantum level in that case. You interact with them. I will skip that, and I will just focus now for 2 minutes about the Thomson scattering. This will conclude my presentation. So, Thomson scattering is a scattering of a wave, of an EM wave by charged particles, so mostly electron in our case. Okay, so this is a scattering of light by electrons. The cross-section is very small. It's roughly the square of the classical electron radius. So it's 10 minus 30 square meter. So it's really small. That means that it will be very difficult to see the light and to capture the light, but it is feasible. So you have two types of Thomson scattering, depending on what we call the scattering parameter. So roughly speaking, the scattering parameter is the ratio of the wavelength of your light, of your laser light, to the Debye length, so to the plasma density. So you compare the plasma density and the wavelength. So if you are at low density, okay, that means the Debye length is very large. So this parameter is very small, and you are in what we call the incoherent regime. So you see free electron actually. Light is scattered by the free electron. They do dominate the spectrum. So if you scatter light on the free electrons, you have access to the velocity distribution function of your electrons. So you have a direct access to energy, what we call the EEDF in plasma physics. Okay, so you have direct access to the energy of your electrons. On the contrary, if the density is large, the Debye length is small, or the wavelength of your laser on purpose is very long, the alpha parameter can be much larger than what, and in that case you are in the coherent or collective regime, and then you will not probe the free electron anymore. You are going to look at the structure in your plasma. So it could be the Debye sphere, but if you have a magnetized plasma with turbulence, you will have access to the turbulence. You will see the wave. You will have access to dispersion relation. I'm not at all an expert in that. My colleague Selina Chiketa is a real expert in that technique. It's quite complicated too, this collective Thomson scattering, but it gives you access to structure, wave, turbulence, and dispersion relation. So it's very important in our field to better understand, especially the anomalous electron transport. So now I will just show you an example of outcome of incoherent Thomson scattering. This is a typical optical bench for incoherent Thomson scattering when we want to look at the EEDF. Nothing really special. You have to be careful when you set up your collection branch to be sure that you probe the direction you want to probe, okay, because of this very bizarre arrangement of the wave vector. You have to get rid of all the stray light because photon that can be scattered by the particles, and that's what you want, but they are also scattered by all optical components, by the walls of your chamber, by your thruster itself, and so on and so on. And this will dominate. So you have to be very, very careful and try to reduce the amount of what we call stray light very, very strongly. If not, you will never be able to see your Thomson spectrum. And then you have to use some very specific and state-of-the-art filtering technique to be able to remove not only the stray light, but the Rayleigh signal. Because on top you have the Rayleigh signal. You always have Rayleigh scattering as soon as you have particles. So you have to get rid of the Rayleigh part also. So at the end, I show you an example here of measurement in the cathode plasma beam. So you see the cathode on the left, and you have the outcome of the Thomson scattering measurement on the right. And this gives you the velocity distribution function of your electron. And from this plot, you have access to the electron density directly, after calibration, of course, and the electron the temperature. And of course, if you have also strong departure from equilibrium, you should be able to see them. Although it's a bit complicated because it will impact the wings, but you should be able to see them. And typically, I think now Sedina is able to go down to 10 to the 17th, 10 to the 18th even per cubic meter as a detection limit, so it's good enough. Maybe below that nowadays, because she improved the system. So it's again enough for us to have, I think, very important information about electron properties in our plasma. And contrary to probes, although probes are much simpler and easier to use, you do not disturb at all, or you weakly disturb, so you can really neglect the disturbance you are introducing in your system. So this is basically a summary with the main ideas, an overview, what we can do, and why it is important to develop this type of technique, of measurement technique, and why we should do it more often. And also, I really want to emphasize on the fact that it's nice to do measurement, but if you don't compare the measurement with theoretical model and with numerical outcome, it's not so useful to make any progress in physics, in our field, and in science in general. So I will stop my presentation here. So this is a bibliography in which you can find many, there are dozens of references. So you can learn a lot about laser spectroscopy and Thomson scattering. And once more, I'd like to thank the University of Carlos III in Madrid and the group of Eduardo for being here today. I'm really enjoying my time, and also want to thank the support, Santander as the support for the Chair of Excellence. Thank you very much for your attention.
Questions?
Okay, have one. So, no, it's okay. I will just sorry. Regarding the time and accuracy that you can have for the measurement, so you spoke about the spatial accuracy, but I guess that if the signal is too weak, you need to integrate that for a long time, so you don't have enough time resolution.
No, this is very tricky, and it depends also on the type of laser you are using. So the spatial resolution can be extremely small, hundreds of micrometer range. So this is good enough. For the spatial resolution, yeah, it's really tricky. So as you said, I mean, if you look for a very short time, the number of fluorescence photons will be small, so it will be very difficult to have a good signal. So you can do what we do, or similar technique like counting the photon. You really count the photon one by one. Okay, so this you can be extremely accurate doing that. You count them and you know when they arrive. You can have a nanosecond time resolution then, but it's a bit long because you do some statistics, of course. Is it a laser-induced photon or just a natural photon? So you have to do some statistics to distinguish between them, but it works. We've been able to do measurement up to almost 1 megahertz with this technique, but I think this is one kind of upper limit. If you want a better time resolution, then you have to use a pulsed laser because they can be extremely narrow, typically nanosecond, but nowadays you have picosecond and femtosecond laser pulse. So then you have an excellent time resolution. But since you are limited by Heisenberg, it also means that you are not so well resolved in wavelength. So there is a kind of compromise, but still you can use a nanosecond laser pulse, so you have again a nanosecond time resolution. So I would say typically with classical technique we are in the megahertz, gigahertz range. So for us in our field it's good enough, I think, for what we do. So we can almost resolve the plasma frequency. It's more complicated so this is true for LIF. For Thomson scattering, it does not work because the signal is extremely weak. So you really have to integrate for a very long time. I think the example I shown you, in the example I shown you, the integration time was something like 10 minutes. So you can only have time resolution if you have a periodic change in your system, because then you can synchronize with the time variation. But if you don't, then you will not have time resolution with Thomson scattering or any type of scattering technique.
Okay, thank you for the talk. First of all, it was very interesting. I had two questions. First one, I didn't understand quite well why for the LIF spectroscopy, you had a need for calibration. And the second question I have is more a curiosity. Is there any non-intrusive technique that doesn't depend on light measurement?
I don't think so. But if you know one, it would be very interesting. No, probably not, because light-based techniques are weakly intrusive because of the momentum of the photon. So I don't think there are non-intrusive techniques that do not rely on the use of light.
Higher frequency ranges, it's not light like this one.
Yeah, but by light I cover from gamma rays to radio frequency. It's very broad, of course. But basically, you have to use photon, I think. For answering your first question, it's a very good one. It was not at all obvious from my. I will go back to the first equation. You will understand. Blah 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 blah. So if I look at this equation, first, it means that if you want an absolute number, you have to know all the Einstein coefficient with a good accuracy, the lifetime, and the cross-section. Okay? Why not? But there is a constant that I call K in this equation, and K is related to the experimental setup, because you have to know the transmission of your optics, the quantum efficiency of your detector, and so on and so forth. And in fact, you have to calibrate mostly because of this constant that is unknown, actually. So you have directly access to the relative density, but to have an absolute number, you have to calibrate using a known gas or using another technique or chemical technique or whatsoever. And typically, the accuracy you have is 50%. It's difficult to be better than that. 50. Already, if you have 50% accuracy for your number density, it's already good. Calibration is extremely complicated, as usual. But for us, a factor of 2 is not bad. Huh? In plasma physics, a factor of 2, it's okay. I'm not talking about a decade. I'm talking about a factor of 2, so it's not bad.
Maybe another curiosity. So I guess that it doesn't really matter the angular position where you have your detector for LIF. I guess the light that is emitted by the fluorescence doesn't have.
No, it's emitted in 4 pi steradians.
Perhaps the Zeeman effect or the Stark effect have to do a little bit with the direction.
No, what counts, in fact, it's not obvious, but everything, in fact, depends on the first step, the absorption. Okay, the rest is you don't care. So what you really probe is the absorption profile and what is happening during this step. Okay, so for the Zeeman effect, you're right. So it means it only depends on the direction of the laser with respect, not the direction, the polarization of the laser with respect to to the magnetic. It's the polarization that counts for Zeeman, not the direction. So yeah, you have to be careful, and that's also a way to be more accurate. That's why I told you that if you want to be very accurate for Zeeman, you have to choose the right transition, not a complicated one. So one that has no hyperfine structure and so on. And you should also select the polarization with respect to the B-fit direction in such a way that you only excite one type of component, just to have less subcomponents. So it would be the fit would be more accurate. So yeah, for Zeeman it's important. For Stark it has no impact for the Stark effect.
You have shown a 2D plot with the velocity and the axial position. How much did it take to measure this? Because I understood that every single point takes like more than 10 minutes. So
you mean the velocity distribution of xenon ions in a Hall thruster? We did that often. 1 week, 2 weeks. What is complicated here is that the velocity range we probe, you see, is roughly 20 kilometers. You cannot scan it in one step with the laser, because the laser is not stable enough. So you have to split it in 2 or 3 steps, and realign your laser, recalibrate the laser each time. So that makes it very, very long. That's why it's so long. Okay. Now, for instance, if your velocity distribution, for instance, this, you see the velocity range is very small. We can scan it in 1 step. So if we would have this type of things, and to make the same 2D map with this type of velocity range, 2 days, 3 days. Depends also on the stability of your plasma, of course. So it really depends on, can you probe the interior distribution function in 1 step? Usually you cannot, if it is very broad. Otherwise, of course, it depends on the signal, of course, that you have, because it will define the integration time. It depends on the stability of your discharge. It's a matter of days or weeks, maybe, depending on what you want to do. It's not a probe measurement. Huh? It's usually longer. Usually what is quite annoying here is because you need quite a long time to do your measurement, the plasma source has to be stable enough. And that can be complicated. It might be complicated to operate it stably, especially when you work with lab thruster prototypes. They are not space qualified. If you use a space qualified thruster, usually it's quite stable. But in our case, a lab model, a first prototype, so it makes measurement even longer.
Can you explain again the origin of the part 2? You said that the aliens coming
Yeah. You know that the whole thruster has an annular shape. Okay, so we measure on the channel axis on one side, but because the divergence of the beam is not 0, at one point you see ions coming from the other side. They cross your measurement axis.
But you are plotting the axial velocity, so not the radial velocity.
No, but they have an actual component too. Because they arrive with a vector that is like that, so they have a radial component and the actual component.
But the axial component is inverse?
No, they go the same way.
Yeah. Okay.
With a smaller actual component.
That's why. Okay. Now I understand.
They are not as fast, they are as fast actually, but you only see one of their components in the direction of the measurement. So. Yeah, actually they come from all the directions. Actually, you don't know, but you don't know where they come from, because it's a scalar product. But they come from, but mostly probably from the opposite side, because it's really quite symmetrical. You should have the same in a cylindrical Hall thruster. It's symmetrical with respect to the axis too, so probably it's less pronounced, I don't know.
Well, Stefan, it's a pleasure to have you here. You pass a talk on a subject that is quite unfamiliar for the background of most of us. It's very valuable. Indeed, we should have more talks on this subject. Then for us, it's very nice that you have come here and that we can do these measurements with our prototype that we have here. Okay. Also, we are cooperating in several projects, and we are quite confident that we could do a propose of comparing medical results with what we are high need for us and for the rest of the community to try to understand better the physics of contrast and contrast. So it's very nice that we have this. I have one comment or one question on the slide you presented on the magnetic nozzle. That is from Benjamin, not from you.
Yeah, it's from Ben.
So can you say that the ions tend to align with the magnetic nozzle lamp?
That's my feeling.
So they try to attach instead of detach.
Yeah, this is surprising, yeah? You clearly see the acceleration from the throat. This is obvious because the velocity is given by the length of the arrow. And I think they tend to align.
But because they are accelerated. When they have a small velocity, they also have a larger radial component.
We have seen this in some data that in the external region, you get an electric field that is pointing inward. So this is what causes the curvature inward of the.
Yeah, at the beginning, the divergence
is very interesting.
Yes.
So actually,
Yes, but I think this is for another reason. This is because of the mode.
What Mario says actually is in a simulation. You have an initial radial electric field that confines, so you get a lower divergence at the beginning. Then there will be a detachment.
then they probably detach further downstream. By true.
The electric field is always radial. It's more independent where you practice.
But of course, it probably depends on the nozzle, on the source itself, on plenty of things. So. No, but I think in the paper it's quite a comprehensive paper. It's a very good paper, and I think they give the density.
Here you cannot say how dense the plasma is.
No. And to the best of my knowledge, this is the only paper showing LIF measurement in the magnetic nozzle. And it's pretty new. 2 years ago, they did that.
Is it in one of the papers that you put at the end?
Yeah, because I give this one because many papers about leaf and Thomson scattering are in the two reference that are paper I wrote in the past, but this one was not included because it's new, so I give the reference at the end. This is the third one. Yeah, it's very recent. So this is basically what we are going to do with the HPT here. Maybe not this time because this is the first time we try, but next time. Anyway, I'll be staying until the end of Sherazad if you want. No, it's what will be difficult in a pulse thruster, PPT, VAT, is that you don't know where the plasma will be exactly, first. This is especially true for VAT, because the arc is constantly moving. And for PPT, I can imagine that the discharge is also a very specific dynamic. So this might be tricky to have the maximum of the signal. But Basically, you can see it as a time average measurement. So you will average over many pulses. This gives you the average behavior over this number of pulses. Unless you can resolve the pulse, because the density is super high. So maybe one pulse is enough. And of course, because we plan to do that on that, if you want to do it in an arc plasma, you have to find a geometrical configuration when you really stabilize the plasma. So not maybe the configuration you are using now, not a real thruster configuration, but a configuration that is really dedicated to do measurement with laser spectroscopy and then to be compared with numerical models. The main concern is the fact that the plasma is not stable in the sense that it is not stable in space. If not, it will work. You have a time average measurement. But I think we can do it in one pulse. Density is so large. It should work. Okay, another try. Something else to try. This would be great. I don't think it has been done ever. No. Thanks a lot. Thanks, you guys. It's also a pleasure to be here, actually, to be in the group, to be at the university. I'm really enjoying my time here. Thanks to all of you. I'm also learning a lot. Your talks were really great, guys. Really, I really enjoyed it, and I also learned. You did a good job, all of you. So I'm staying until the end of July. So if you have any question, you do not hesitate. And as Pablo said at the beginning, I will be back next year. So you can also ask questions next year. Okay? You're welcome. Thank you.